All right, let's get started. So today's lecture will be on exploration. And before we start, just a couple of notes. First, homework 4 is due on Wednesday, and that's going to be the last homework. So after Wednesday, all you have to do is work on your final project and do a really great project. And to help you do a really great project, at this point, I believe we've already sent feedback to all of you. And if we haven't, then we'll send it to you shortly. So hopefully almost all of you will have received, by the end of today at least, a response to your project proposal submission. And in the feedback, basically if you turned in a proposal that, according to the instructions, you will get full points on it. And then for some of you, we wrote a couple of sentences with some feedback. Some of them are just suggestions or maybe some pointers to related work that might be relevant, so do take a look at that feedback. And if the feedback says something like, well, maybe come talk to us in office hours or something, please do take us up on that and come and discuss your project a little bit. For almost everybody, the proposals were exactly what we asked for, so that's great. Okay, today's lecture. Today we're going to talk about something called the exploration problem, and I'll start off by explaining what the problem actually is and give you a few illustrative examples. And then I'll discuss this framework of multi-arm bandits, which provides us with a kind of a simple domain in which to study exploration algorithms that are a little bit more theoretically grounded. So we'll go through a few different exploration algorithms that are suitable for multi-arm bandits. And then we'll talk about a variety of extensions of these methods to the kind of complex MDP settings that we encounter in deep reinforcement learning, including optimism-based exploration, posterior matching exploration, and information theoretic exploration that reasons about information gain. So what we'll basically do is we'll discuss these three classes of algorithms in the context of multi-arm bandits, and then we'll talk about how they can be extended to practical exploration methods that we can actually use in the kinds of large MDP problems that we're typically concerned with when we talk about deep RL. So the goals of today's lecture will be to understand what exploration is, basically what's the problem and why do we need to actually worry about it, understand how theoretically grounded exploration methods can be derived in simple settings like multi-arm bandits, and understand how they can be extended into practical algorithms that we can actually use with deep reinforcement learning. All right, so let's get started. So what's the problem? What's the exploration problem? We can illustrate it with a little example. So this is mostly easy. So I think for homework 3, you actually implemented Q-learning for Pong. This is a slightly harder game than Pong, but it's still pretty easy. Like you can set up your favorite Q-learning variant, double Q-learning, whatever, and it can learn to play this game. This game is impossible. Unless you're a human being, you can't play this game. It cannot be done. It's impossible. This is basically one of the hardest games to learn to play with Q-learning in the Atari suite. So why? What the hell is going on here? Why is this so much harder than that thing on the left? So those of you that have played around a little bit with the Atari benchmark suite will recognize this as a game called Montezuma's Revenge. Montezuma's Revenge is I don't think it's actually a very fun game. Like you can get the emulator and you try playing it yourself. It's a little tedious. But basically the way that the game works is that you control this little guy, you run around in this room, and the game consists of a progression of rooms. The rooms are actually arranged into a kind of a pyramid shape. So you start off at the top of the pyramid and you have to progress down, and you win the game when you get to the lower left-hand corner. And each room is completely different. So this is actually the first room, which has these 3 ladders and a skull. Other rooms have different numbers of skulls. Maybe they have a pit of lava or something. So they're all a little different. The rewards in this game are a little bit peculiar. So some things give you a reward and some don't. So if you pick up the key, you get a little bit of a reward. If you open the door, you get a bigger reward. If you get killed by a skull, actually you get nothing. Like it's not a negative or positive reward. And in fact, it's very confusing as to whether killing the skull is actually a good or bad thing because, or when you get killed by the skull actually disappears. So a legitimate strategy in this game might be to intentionally kill yourself to destroy the skull, and then you have an easier time. So it's actually very hard to figure out whether getting killed by the skull is positive or negative. And then finishing the game only weakly correlates with rewarding events. So when you grab the key, you can like open the door on the left or open the door on the right, and different things happen, and it's not clear which one actually brings you closer to ultimately winning the game. Now, we can actually play Montezuma's Revenge fairly well. I mean, it requires a little bit of coordination of your fingers, but it's not actually that hard for humans. In fact, Breakout is probably actually harder for us because we know what to do in this game because we understand what these sprites mean. Like, okay, we haven't had the experience of getting killed by a rolling skull, but we kind of understand that a skull is like a bad thing and a key is something that can open a door. These are intuition we have about the world that we've learned through our lifetime of experience. So to us, these sprites actually mean something. But to the computer, they're completely meaningless. And the computer has to discover all of this through trial and error. And that's why this is so difficult for reinforcement learning algorithms. So to try to put yourself in the algorithm's shoes, let me tell you about a slightly different game, a game that maybe is a little closer to the experience that a reinforcement learning algorithm has when it's confronted with one of these peculiar games. How many of you have heard of a card game called Mao? Raise your hand. Okay, not very many of you. Okay, so I'll explain. It's kind of a fun game. It's very frustrating. So the card game Mao, also, I guess, sort of related in philosophy to something called Calvin Ball. But in Mao, you're told only one thing when you start to play the game, which is the only rule you may be told is this one. And then you have to figure it out. And the reason the game is so frustrating is, well, you get these cards and you try to put some cards down in some order or something, and you just have no idea what you're supposed to be doing. And if you break a rule, not knowing what the rules are in advance, you get some kind of penalty. So maybe you have to draw an extra card or something. And if you've never played the game before, this is very frustrating, and it basically makes no sense. So it seems like you're surrounded by people who know what they're doing, you have no idea what you're doing, and you just get dinged for every mistake you make without really knowing the rules. So you only discover the rules through trial and error. You have to basically attempt to play the game. You're told, no, you played it wrong, incur a penalty, and you're slowly supposed to pick up what's going on. Now, in Mao, there's the added challenge that people can change the rules on you as the game goes, to make it even more frustrating. And the rules don't always make sense to you. In fact, almost always they don't make sense initially. So this, like playing this game Mao, that's basically what the RL algorithm is trying to do. It's trying to interact with this world where it has no prior knowledge, the rules don't make any sense to it, and has to discover everything through making mistakes and trial and error. And beyond just not knowing the rules and having to discover them through trial and error, temporally extended tasks, like Montezuma's Revenge, they become increasingly difficult based on a number of additional factors. One of them is how extended the task is, meaning how many complex things do you have to do in the right order before you receive feedback. And then also how little you know about the rules. So typically in our algorithm, you start off not knowing the rules at all. This temporally extended thing is huge. So imagine that your goal in life was to win 50 games of Mao. So if you win 50 games of Mao, I'm going to give you $1 million. But you don't know this in advance. Like, you just go out into the world, you live your life, you earn your paycheck, you go to the grocery store, and unbeknownst to you, if you were to win 50 games of Mao, you get $1 million. Like, your probability of just randomly doing that, most of you don't even know about this game, is just minuscule. So it's just not going to happen if you interact with the world largely at random. And that's kind of how Montezuma's Revenge is. You have to do this sequence of seemingly arbitrary, peculiar things governed by rules you have no knowledge of. You have to do them in the right order. And if you do all of that, then you get your $1 million and you win the game. So these temporally extended tasks where you don't know the rules, they basically require you to do things that randomly have a very low probability of occurring unless you have some additional guidance, unless you have some additional mechanism that is helping you to explore the world, to try things that are different from what you have tried before. Here's another example. So, enough about games. Let's look at a more of a kind of a continuous control example. This is actually something that Josh showed last week. So these are continuous control tasks where the RL algorithm is controlling this 5-finger hand. So it's a very complex hand. It has many degrees of freedom, and the controller is directly driving the torques in the fingers. If you imagine for some of these tasks, like that ball picking up task, if the hand only received a reward when it actually placed the ball in the right location, or if it only received a reward when it hammered in the nail, its probability of randomly doing this will be minuscule, because random movements of the fingers, they'll wiggle the hand in all sorts of different ways. They might not even get around to picking up the hammer. So this is a setting where, again, unless you have some prior knowledge about where you're supposed to go or some kind of additional guidance mechanism that tells you to explore interesting things, you are extremely unlikely to randomly do these behaviors. And in these videos, what actually happened is that there was a little bit of a human demonstration that was provided to give guidance to the algorithm just to overcome the exploration challenge. So this is another very different example where exploration is a really big problem. Oftentimes in the reinforcement learning literature, we talk about the problem as one of trading off exploration and exploitation. And there are basically two potential definitions of the exploration problem that turn out to be very similar. So the one that I discussed so far is how can an agent discover high reward strategies that require a temporally extended sequence of complex behaviors that individually are not rewarding. So if you don't get little breadcrumbs along the way, how do you figure out that you're supposed to traverse this complicated path? That's what I presented so far. Another way to look at the exploration problem is this. How can an agent decide whether to attempt new behaviors to discover ones that have even higher reward, or to continue doing whatever is the best thing that it knows so far? And these are actually kind of the same problem. So exploitation means doing what you know will yield the highest reward. And if you haven't done a very good job at the task so far, maybe the thing that will yield the highest reward is not actually all that rewarding, but you don't know any better because that's the best that you've ever seen. So if when you're playing the Montezuma's Revenge game, if you've picked up the key, maybe you might reasonably conclude that the best thing in life is to pick up that key. So what you should do is you should kill yourself repeatedly until you lose the game so the key reappears again, and then you can pick up the key again. That's a very reasonable way to exploit what you've learned so far, but you have to trade that off against exploration, which is doing things that you haven't done before in the hopes of getting even higher reward. And this second one has to be a little bit chancy because you don't actually have any way of knowing whether there even is anything better. Maybe the game is set up in such a way that you have to pick up the key and then kill yourself until the key reappears. That wouldn't be a very interesting game, but if you didn't know any better, you might reasonably conclude that's the way the world works. So in fact, this temporally extended problem and the exploitation exploration problem are basically the same thing. OK, so let's look at a few examples of some other things where exploration and exploitation needs to be traded off. You can imagine lots of examples from your daily life. If you, let's say, want to choose what restaurant to go to with your friends for a party, well, you might exploit your prior knowledge, go to your favorite restaurant, or you might choose to explore a little. You might try a new restaurant, and maybe you'll discover something that's much better than what you've known before. So this is a very sensible thing that maybe we have to decide sometimes. If you have a company that's doing online ad placement, you might figure out, well, there's just one particular ad that always gets a lot of clicks. So maybe we should exploit. We should just show the most successful advertisement over and over again. But if we always do that, then we won't actually be very successful because the ads change. Maybe somebody has a new ad, or maybe the user base changes. So sometimes we have to explore and show new advertisements, even at the risk that they won't be as good, so that we can do a better job of discovering which ones really are the best ones. If you're drilling for oil, you might say, well, let's drill in the best known location. This is the location that has yielded a lot of oil in the past. But eventually that oil runs out, and we have to do a little bit of exploration. We have to try new locations, even at the risk of wasting our efforts in places that are not very good, so that we might discover some better ones. So this comes up in a lot of settings where we have to do sequential decision-making in kind of model-free or not fully known, not fully identified systems. Now, exploration is very hard. Exploration is hard from a theoretical perspective, meaning that it is very difficult in complex, unstructured, open-ended environments to define exploration strategies that have any practically useful notion of optimality. So when we talked about, for example, learning policies, we could define a very good notion of optimality for a policy, and we can actually build algorithms that have some hope of finding an optimal or near optimal policy under assumptions like convexity, for example, which might not be entirely reasonable in practice, but they're pretty close to the kind of real-world settings we have. With explorations, getting exploration strategies that are even close to being provably optimal is extremely difficult. So if we ask the question, can we derive an optimal exploration strategy, we have to figure out what does optimal even mean. Even defining that in very complex MDPs can be extremely hard. Maybe we can define it as saying, well, what's the regret that we incur versus the Bayes optimal strategy? So if we're being perfectly Bayesian, if we really maintain a full distribution over our beliefs, that's maybe the best that we can do. So we'll talk about a few ways that we can define optimality for exploration. But even if we can define it, actually being able to set up exploration strategies that even remotely approach that notion of optimality can be extremely difficult in many practical reinforcement learning problems. So what we often do when we work on exploration is we study problems at different levels of complexity, ranging from theoretically tractable to theoretically intractable, so that we can sort of build up our exploration algorithms in the theoretically tractable domains, where we can actually answer some questions about them, and then try to extend them to the more realistic domains, which are typically not theoretically tractable. So the theoretically tractable domains, usually the simplest ones are going to be things like multi-arm bandits, which I'll talk about at length in today's lecture. And you can think of these at a very high level as sort of one-step stateless RL problems where you just have to choose an action. There's no state, there's no sequence. So we'll talk about this more. Contextual bandit problems, which are one-step RL problems that do have a state. Small finite MDPs, so the kind of MDPs where you could, for example, run value iteration and get an exact solution. These allow for some amount of theoretical analysis, but not as much as the bandit problems. And then on the extreme end of the theoretically intractable side are the kind of MDP problems that we typically concern ourselves with in this class, which are large or infinite MDPs, continuous spaces, or extremely large spaces like images that are still discrete, but so large that the discrete structure is not really useful to us. So these are the ones where we actually want to have the exploration strategies, and the ones over there are the ones where we can actually develop these exploration strategies and get a little bit more of a theoretical backing to understand which strategies are more likely to be useful. So we'll start by discussing these, by discussing multi-arm bandits, talk about some exploration strategies that work in those domains where we can get a little bit more of a handle on why they're good, and then we'll discuss how they can be extended in this setting where they'll largely take on the role of a heuristic, but a heuristic where we have good reason to suspect that it might work well. Okay, so what makes exploration problems tractable? With things like multi-arm bandits and contextual bandits, what we'll see is we can actually formalize exploration as the problem of identifying a partially observed Markov decision process. And because we can formalize the problem in this kind of reasonable way over here, we can actually write down what we need to do in order to identify that PUMDP, what are the complexity of these strategies, and actually derive some bounds on the performance of exploration algorithms. Because these settings are so simple, because they're, in the case of multi-arm bandits, they're stateless one-time step problems, actually learning the policy once you've identified the MDP is trivial. You just pick the action with the largest reward. Small finite MDPs, there you can frame, for example, exploration as Bayesian model identification and reason explicitly about the value of information, because these MDPs are smaller and you can enumerate all the states. So there's some theoretical analysis for small finite MDPs. We won't go into that in this lecture, but that's something that we can also do. And in the larger infinite MDPs, like Montezuma's revenge, optimal methods generally don't work in that they're not optimal, but we can take inspiration from the optimal methods in the smaller settings and the settings up here to develop heuristic methods that we still have some intuition for and that we think might work well. So that's going to be the general flavor of how these exploration strategies are going to work. All right, so let's talk about bandits. And we'll start talking about bandits because they're relatively simple. They allow us to build our intuition about exploration. And then in the second half of the lecture, we'll extend to the more general deep RL setting. So what's a bandit? That's a bandit. That's a guy with a gun who's going to steal your money. But what a bandit really is in the context of this lecture is it's kind of the Drosophila of exploration problems. It's like the simplest model system that we can construct that still gives us the general flavor of an exploration problem. So the Drosophila is a fruit fly, often used as a model system in biology, and the bandit is often used as a model system in exploration. And the term bandit doesn't actually refer to this guy. What it refers to is this thing. So this is a quaint sort of Americanism. You call this a one-arm bandit. It's a slot machine, and it's called a one-arm bandit because it has one arm and it takes your money. So in a one-arm bandit, your action space consists of one action. You can pull the arm. You can't choose not to pull the arm because I guess this is modeling people who are sort of compulsive gamblers. So you have to pull the arm, and you get a reward for pulling the arm. So the one-arm bandit is not actually very interesting because all you can do is pull the arm and get or not get a reward. What's a lot more interesting is a multi-arm bandit. So you go in a casino, you see a whole row of these things, and you might wonder, well, if I go play that first slot machine, maybe that one is a little better than the rest. Maybe that one has a slightly higher chance of giving me the money. So you have a number of different actions. You can pull the arm in any one of these slot machines. And the game is that the different arms will actually have different payoffs. And in fact, we'll complicate this a little bit. These are slot machines. They're not deterministic. So every arm actually has some probability of producing a particular payoff. So every arm is itself stochastic. Its rewards are distributed according to a particular distribution, but that distribution is different for different arms. And now you can actually play this game. Now it actually gets a little bit fun because you have to actually play the different arms of the bandit to try to find the one that has the highest average payoff. If you know the distribution of the different arms, the best strategy is obvious. If you know the distribution, just pull the arm with the highest average payoff, because that's going to be the best possible thing in the long run. But when you start off, you don't know the distribution over the reward of each arm, so you have to play around a little bit. You have to basically spend your money maybe playing with suboptimal slot machines to try to find the one that is actually the best. So this is the multi-armed bandit. OK, so we have an unknown per action reward distribution. And we can play. Let's play with some bandits. So what we'll do here, we'll have a little kind of audience participation thing. But before we do the audience participation, I need to brief you on what this is going to be, because this is a life or death situation. What we're going to do, we're not going to play with slot machines. We're going to, well, this maybe, I don't know, if you have a very cynical view of the medical profession, you might call this a slot machine. We're going to play drug prescription. So this is the drug prescription problem. In the drug prescription problem, your arms are different drugs you can prescribe. So you're a doctor, you have 4 drugs, the patient comes to you, you have no idea, you're not a very good doctor, you don't actually diagnose them, you just prescribe a drug to them. And you get to choose one of these 4 drugs, and so those are the arms. Each drug is an arm. And the reward, well, your reward is going to be a little morbid. It's going to be 1 if the patient lives and 0 if the patient dies. So this is not a bandit that gives you money. This is a bandit that gives you living or dead patients. So the stakes are kind of high. So every time if you're not sure which drug to prescribe, you need to try something, but someone's going to die because of it. So how well can you do? Let's actually do this. These are not real patients, so no one's actually going to die. OK, so everyone can see that? OK, so the experiment has started. The first patient presents with some symptoms. You have no idea how to interpret those symptoms, so you're going to pick a drug at random, and we're going to raise our hands. So everybody who wants to prescribe drug 1, raise your hand. Drug 2, drug 3, drug 4. OK, clearly you guys know something I don't. All right, so drug 4, the patient, it's a little hard to see, but time step 1, drug 1, the patient dies. So you guys have all killed your first patient. There's 20 of them, so you still have a few to play with. All right, patient 2, drug 1. Drug 2. Drug 3. Drug 4. Cool, OK, so drug 2 is the winner. The patient also dies. Let's try the next one. 1, 2, 3. OK, I think I know which one it's going to be. OK, also dies. Now remember that this is stochastic, right? So you might actually pick the right one, and the patient might still die. All right, let's go with the next one. 1, 2, 3, 4. OK. All right, patient lived. OK, so shall we try 4 again? Raise your hand if yes. OK, that's what I figured. Lived again. Shall we try 4 again? OK. Patient lived again. Drug 4 again? Not the majority. How about drug 3? 2? 1? You have a question?
No.
OK. All right, so it looks like 4 still wins. OK, 4 lives. So what do you guys think? Shall we just go with drug 4 until the end? Yes? OK, let's just go with drug 4 until the end. All right, looks like you guys actually got this right. All right, so here's how we did. This is our drug efficacy. So we tried, this is the ground truth. This is what we were not allowed to know. So it turns out that the actual efficacy of the drugs, you guys actually went in like reverse order. You started with the worst one and then got to the best one. So 1 is the worst and 4 is the best. Now, what you see in this graph here is the performance of different strategies. So the purple one, the one that looks like a straight line taking off, that's what you guys did. The other lines are other strategies for exploration, and we'll actually talk about some of these. So the kind of cyan one, the light blue, that's upper confidence bound, and we'll actually talk about that next. The yellow one is posterior sampling. We'll discuss that also. And then red is epsilon greedy. So epsilon greedy means you basically pick arms at random with some probability epsilon. And that one didn't do so well here because there was one arm that was so dominant that really the whole problem was about discovering the dominant arm. And green is the greedy strategy that just picks this whatever arm it thinks is best. And green actually did pretty well here. And you guys actually also had a pretty greedy strategy, so that just happened to work out well in this case. All right, so that was fun and exciting, and we only killed 3 patients. Last year, a lot more died. All right. So let's think of some mathematical definitions that we can use to actually think about exploration algorithms for bandits. So we're going to assume that the reward of some action, that there's a finite number of actions, and the reward of an action is distributed according to some probability distribution parameterized by parameters theta. So for example, in the binary reward case that we had before, where the patient either lives or dies, theta might just be the probability that they live. And then 1 minus theta is the probability they die. So we have some parameters that will identify these distributions. And we'll assume some prior. So we'll assume that at the very beginning, the parameters for every arm are sampled from some prior p of theta. If theta is just the probability of the patient living, maybe p of theta is just a flat prior. So it doesn't necessarily need to be very informative, but in general, there's some p of theta. And then what happens is that this formulation of the problem actually defines a partially observed Markov decision process where the state consists of the parameters of these distributions. Because if you knew the parameters of all the reward distributions, you can figure out the expected reward of each action and just take the best action. Now, in reality, you don't know this. So this is the state of the PUMDP, but you don't know that state. And the best you can do is maintain a belief state. You can maintain your estimate of the distribution over the thetas. And if you formulate the problem like this, you could actually derive an optimal exploration strategy. So you could solve the PUMDP to yield the optimal exploration strategy. This is kind of overkill because the belief space is still huge, and there are actually much simpler strategies that you can exploit to still get very good results. In fact, you can find strategies that are provably have the same order of regret as actually solving the PUMDP. So you can use the PUMDP to sort of build up your conceptual framework of how these bandit problems work, but in practice, you don't actually need to solve the PUMDP, sorry, to get a good exploration strategy. So we can do very well with much simpler strategies. Now, what does very well mean? We do need that measure. We need some way to measure how good an exploration strategy is. And when we talk about bandits, the way that we measure how good an exploration strategy is by using something called regret. So when you killed all those patients, you might regret having killed them, and that's the thing that you want to minimize. So regret is the difference from the optimal policy at a given time step. We can formally define it like this. The regret at a given time step t is the value of the optimal policy, which is just t times the expected value of the best arm. So if you knew a priori that drug number 4 was the best drug, this would have been the expected value of arm number 4, which I think was around 0.9 in that game, times the number of time steps, which was 20. So that would have been the best possible thing you could have done if you were omnipotent. And then you subtract from that how well you actually did. And these are the rewards of the actual arms that you pulled. Now, the regret of the optimal policy in expectation is 0. So this is the expected reward of the best action, and this is the actual reward. In expectation, this is 0 for the optimal policy. Not for the optimal exploration strategy. A regret of 0 might be impossible for exploration, but if you're omnipotent, the expectation of this would be 0. Any single run might not be 0 because these are your actual rewards. Remember that even that best drug, even that drug number 4, it still had a 10% chance of killing a patient. So even if you already knew which drug was best, you might still have gotten a slightly worse reward. But if you don't start off knowing the true answer, then the optimal exploration strategy might have a regret greater than 0. So we measure how good an exploration strategy is by how good the regret is, which is to say how much worse is it than the omnipotent player that knows how well each arm does. OK, so what are some strategies that we could use to get low regret? There are a variety of relatively simple strategies that we can employ. We can often provide theoretical guarantees on the regret in these multi-arm bandit settings. And there are actually a variety of algorithms that are optimal up to a constant factor. But empirical performance might actually vary. So you might actually have an algorithm that is provably optimal, and optimal means O of log of t regret, and you have another algorithm that's also O of log t, but in practice they might be different. That constant factor might actually result in different empirical performance. So it's not enough for us to just find one provably optimal exploration strategy. We do still want to have a number of different options. So exploration strategies for complex MDP domains will basically be inspired by these strategies. So let me present, in this lecture I'll present 3 classes of strategies. There are many more, but I'll present 3 of them because then I'm going to talk about some deep RL strategies that are sort of inspired by these. So the first one, and this is probably the best known exploration strategy for multi-arm bandits, is optimistic exploration. So at a very high level, the family of optimistic exploration strategies, they all look basically like this. You keep track of the average reward for each action. We're going to call that mu hat A. If you have mu hat A, then you can do the maximal exploitation thing. You can say, let's always pick the A that is the argmax of mu hat A. Let's always pick the A that has the highest mean. That's a pure exploitation strategy. That's the greedy strategy when we played that medical diagnosis game. Now, the greedy strategy is not always good because it doesn't explore. So what we can do to encourage some exploration is to instead use an optimistic estimate, where we'll argmax mu hat A plus some notion of uncertainty. So, for example, we might have some constant times some kind of variance estimate. And there are different ways that we can estimate this thing. There are a variety of different strategies that we can use, but they all have some flavor of saying, if you're not sure how good this arm is, let's sort of artificially inflate its goodness to encourage you to try it. Or put another way, we're going to try all the arms until we're sure that they're not great. If you have some arm where you're not sure how good it is, you'll just assume that it's great until you know otherwise. One example of an algorithm that has been very well analyzed in theory, that's one of these optimistic strategies, is the upper confidence bound, or UCB method, which uses the following measure of uncertainty. So in this algorithm, it's a very simple measure of uncertainty. You just take the average return that you've seen from that arm, and then you add the square root of 2 log t divided by NA. So NA is the number of times that you've picked this action, and log t is the log of the number of time steps so far. So the intuition behind this bonus is that if you've picked an arm very few times, then the square root of 1 over that will be big. So this encourages you just simply to pick arms that you haven't picked very much. It's not even looking at any notion of explicit variance. It's just looking at how many times you've picked an arm. And it's saying, if you haven't picked this thing very much, do it more. And it turns out that even with this very simple counting-based reward bonus, you can actually show that the regret goes as log of t, which is provably as good as any other algorithm asymptotically up to a constant. So O of log of t is actually the best that you can hope for in general. So yes?
So how should we understand this add here? Because before it is argmax and it's say integer, and on the other side is just maybe some number, real number.
So this is a number that depends on A.
Yes, but then when we do the square root, we get some float number to point.
Mm-hmm. Yep.
Then if our action is only like allowed in integer, then it thinks we have.
Oh, I see. So this is not an integer. This is the average reward that you've seen from that arm. So let's say that you have 4 slot machines. And the first slot machine, you've pulled the arm twice, and the first time you got $1.5, and the second time you got $2.5. You say, okay, its average reward is $2. And then you take $2 plus this quantity, and you get some other real valued number.
Oh, okay. So argmax is the whole thing.
Yeah, sorry. This is argmax like this. Yeah, thank you. Okay, any other questions about this algorithm? So this algorithm is a very simple algorithm, but it's very important to understand because this is the foundation of many, many other exploration strategies. Okay. Let's talk about another exploration strategy. So remember, I mentioned before that even though there are multiple exploration strategies that can be proven to be asymptotically optimal up to a constant, they might still have different empirical performance. So it helps for us to have a few different exploration strategies that we know about so that we can try them and see empirically which ones actually perform well. So there is another strategy that we can think about, and we'll discuss also some deep RL strategies based on this, which is sometimes referred to as probability matching or posterior matching. So the idea in this strategy is the following. Let's go back to that PUMDP formulation that I discussed. And let's say that you maintain an explicit belief state, p hat of theta 1 through theta n. How do you maintain it? Well, I don't know. Maybe you choose some distribution for these thetas and you assume they're independent or something. You just choose some parametric class of distributions, whatever your favorite probabilistic model there is. And the way that we're going to explore is we're going to say this p hat, this is actually a model of our bandit. So this p hat models the problem that we're trying to solve. In fact, it's a distribution over models, because any theta 1 through theta n defines a bandit. It may not be the true bandit, but it's a potential bandit. And the p hat of these is our distribution over these parameters. So what we can do is we can actually sample a bandit from this distribution over bandits, pretend that this is the true bandit, and pick the optimal action. Why might this be reasonable? Well, let's say that your distribution over one of the thetas is very precise. Like maybe for one of the arms, you've pulled it many times, and you're certain, you know what that theta is. Then no matter how many times you sample from that distribution, if you're sure that that theta is bad, for example, maybe you'll just never pull that arm. So sampling these thetas is a lot better than just sampling random actions. Because when you sample these thetas, the really silly stuff, the stuff that makes no sense, you just won't do it. And if you're sure that some arm is really good, you'll always pull it. So sampling your models from this model distribution is much better than sampling actions entirely at random. And then after you take that action, you're going to actually update the model. There's another interesting thing that happens when you sample these models from your model distribution, which is that if you have some theta that you're very uncertain about, you'll actually try many different parameters for that theta. And if that theta might be good, you'll eventually sample that, and you'll eventually try that arm. So when you sample like this and you update the model, you will actually resolve the ambiguities in your model in the places that matter. And you'll also be strategic about it. So if you have high uncertainty over some theta, but very low uncertainty about another theta that's definitely better, then you don't need to resolve that uncertainty about the bad theta, because you know that even wherever it is in its uncertainty region, it's probably worse than the best one. So you can be a little more strategic, yes?
So do you also, so is the P of theta, is that like a prior, or do you also?
No, this is your model, so you update this. So when I say update the model, it means update p hat.
Okay, so then the draws from that are not also the model? So,
Okay, so this is a model. This is a distribution over models. So every theta 1 through theta n, every time you draw a theta 1 through theta n, that fully determines a bandit. This thing, it's one more level of uncertainty. This is actually a distribution over models.
okay, so then you update both every.
You update this thing. You update p hat, and then you sample the thetas.
Very good.
Yeah. Yes?
It sounds like the best strategy has something to do with the number of trials you get to do. Because if you're going to get one trial, then every
Yes.
strategy would be the same.
That's right. So this, I should say that for this kind of analysis, I'm talking about the cumulative regret. So the cumulative regret assumes that you're going to play for a really long time. There's a different way to analyze a bandit exploration algorithm, just called simple regret, which just refers to the regret of a particular time step. And we're not talking about that here. So if you want to learn more about bandits and you want to look up simple regret, there's actually very different analysis that studies which algorithms will be better if you have very limited time. Yes?
Do we initialize like the distribution random uniform at the beginning? Or?
Well, so this is your modeling choice. So you need to somehow model p hat. Usually what you would do is you would try to initialize it to the prior and then update it. But how you actually do this is kind of up to you. So you choose some kind of probabilistic model. You choose your favorite update method. If you are being truly Bayesian, meaning that your updates are doing the correct Bayesian thing, integrating the evidence and the prior, then this algorithm has some nice properties. In practice, you're doing some approximation, and all the guarantees go out the window. But you do your best for this, right? OK, so this is the probability matching or posterior sampling approach. And and you update the model, and you repeat this process. This is also sometimes called Thompson sampling. So in general, if you see some scheme like this, you have a distribution over models, you sample a model, act under that model, and update the distribution, that is typically called Thompson sampling. It's hard to analyze these kinds of algorithms theoretically, although I think the intuitive interpretation where we say that, well, even if you have uncertainty over one of the thetas, if you know that some other one is better, you'll just pick the better one. That kind of makes a lot of sense to me, and it seems reasonable to conclude that these algorithms might have smarter exploration strategies. And empirically, they can indeed work very well. So if you want to learn more about this, check out this paper, An Empirical Evaluation of Thompson Sampling, and there are many other papers that study these types of methods. So this is kind of, you can view this as a more model-based way of doing exploration, whereas the upper confidence bound is a bit simpler. Okay, any other questions about Thompson sampling or probability matching or posterior sampling? Okay. And the third strategy that we'll talk about is based on information gain. So this one is even more model-based. This one is going to reason about the additional information that you'll gain from taking certain actions. So in order to start thinking about information gain, one of the things that it helps to introduce is something called Bayesian experimental design. So let's forget about bandits for a second. Let's say that we want to determine the value of some latent variable z. So we don't know what z is. Maybe we have our belief about z some distribution. So z might be the optimal action, or the value of the optimal action, or the parameter of some arm, some kind of property of our system. Then which action do we take? Well, let's say that we have a belief over z that's going to be denoted p hat of z. So p hat of z is our current belief about z. And the entropy of p hat of z basically tells us how uncertain we are about it. So if p hat of z, maybe z is a continuous value, p hat of z is a Gaussian, then the entropy of that Gaussian is going to be bigger if it's a wider Gaussian. And then we'll let h of p hat of z given y be the entropy of our estimate after we observe some other piece of information y. So if y tells us something about z, then probably after seeing y, we'll have a lower entropy estimate of z. So different observations will give us different amounts of information, and they'll hopefully reduce our entropy. So in a bandit, for example, y might be the reward of some arm. So the lower the entropy, the more precisely we know z. So what we can do, if we want to write down a criteria for how good a particular experiment is, we might say that an experiment is good if it gives us a lot of information about z. So we can formulate this quantity called information gain, which is the expectation under y. So we have some belief about what kind of y we'll get. Expectation under that belief of the entropy of p of z now minus the entropy of p of z after we observe y. So this is a little bit circular. It's like saying we have some belief about how the world works, and under those beliefs, we can guess how much information we'll gain if we get an observation according to those beliefs. Now, those beliefs might themselves be incorrect, but this is the best estimate that we can get based on our beliefs of how much information we'll gain about z. Now, in reality, these observations y are, of course, a consequence of the actions that we would take, so this whole thing has to also be conditioned on the action. And that's how you can actually choose the actions to conduct your experiment. You might say, I have some belief about which observations I'll get given certain actions, and then I will update my z's based on those observations so I can integrate all of these things and figure out the information gain that I will get for a particular action about a particular variable z. So if we're thinking about this as a sort of experimental design, this can be the Bayesian, the optimal way to write down a criteria for how much we'll actually learn about our system from taking particular actions based on our current beliefs about that system. So we can use this to actually derive a number of different bandit exploration algorithms. I'll briefly present one of them. I don't want to go too much into the details because the particular details will actually be different for the DeepRL case, but just to give you a little bit of a flavor of how these things might work. So this is a very, very brief summary of learning to optimize via information-directed sampling. And what they do in that work is they say, well, my observation is going to be the reward. My z, the thing that I want to learn, is the parameter of the bandit. And then they're going to write down the information gain of an action as the information gain about the parameter of that bandit from observing the reward. And of course, they don't know what reward they're going to observe, so they have to use their current estimate of the bandit to figure out the information gain. Then they'll write down a second condition, which is the expected suboptimality of that action. So based on what you know about the bandit now, you can compute the expected value of the difference between the optimal reward and the reward you'll get from that action. So that's sort of how bad that action is. And then the criteria that they use for exploration is the ratio between the squared suboptimality and the information gain. So the intuition here, this quantity is minimized. The intuition here is that if an action is really, really suboptimal, don't take it no matter what you'll learn. But if you won't learn anything from taking an action, then don't take it either. You'd rather take actions where you'll actually learn something. So this is a particular exploration rule that they formulate and analyze in this paper. There are other ways to use information gain also, but this is just the one that's in that paper. Yeah.
Did they just make up this equation, or
well,
is it derived?
no. So then they analyze its theoretical properties. So basically, can you bound the regret when you have this kind of exploration rule? Generally, when you read the Bandit literature, a lot of methods have this kind of flavor where they write down an exploration rule that's seemingly arbitrary, but the aim is to then show some kind of bound on its performance. Okay, so the intuition here, don't bother taking actions if you won't learn anything, but also don't take actions if they're too suboptimal. Okay, so this is maybe less important for us. This is just to give you an example, but the important bit from here is this information gain criteria and how we can use that as an exploration rule for optimal experimental design. Okay, so just to summarize the general themes, we talked about upper confidence bound, which means basically pretend that the arm is better than it is and inflate its value based on your uncertainty or based on the variance or the inverse of the number of times you visited it. Thompson sampling, which means try to model your belief over the MDP, sample MDPs from that belief, and act greedily with respect to that sampled MDP. And information gain, where you try to actually quantify how much you'll learn about the system from taking certain actions. Most of the exploration strategies that we've discussed require some kind of uncertainty estimation. Even if it's very naive uncertainty estimation like over here, like this 1 over n, that's still an estimate of uncertainty. It's just a very crude estimate of uncertainty. It's saying if you haven't done it many times, you're probably uncertain. Usually, these exploration strategies assume some kind of value to new information. So this is a very fundamental thing in exploration. If there's no value to new information, then there's no point of exploring. And some of them might assume that unknown equals good. That's optimism. They might assume that a sample is the true model. That's the Thompson sampling. Or they might assume that information gain is good, which is the rightmost one. So there's some kind of criteria that needs to drive you towards new information, and typically you need some kind of uncertainty estimate measure in order to figure out what's new. All right, why should we care about these things? Well, bandits are easier to analyze and understand than really complex MDPs, so this is a good place to develop some strategies. We can derive foundations for exploration methods, and then apply these methods to really complex MDPs. There's a bunch of other stuff relating to exploration theory that is not covered in this lecture, but if you want to learn more about it, I just want to tell you that it exists. So a lot of the literature on bandits analyzes things called contextual bandits. So far, we talked about bandits where you just choose an action and you get a payoff. A contextual bandit is where you get a little bit of evidence. So maybe you go to the casino and you look at the slot machines, and you've learned something about slot machines. Like you've learned that slot machines that are red give you more money than ones that are green or something. So that's a little bit of context that you have. So in a contextual bandit, you actually get a little observation, and then you choose an action. You can think of this as an MDP where you have states and actions, but you only have one time step. So the action doesn't actually affect the next state. Whereas in regular multi-arm bandits, you don't even have a state at all. We didn't talk about this, but there's actually quite a bit of analysis that can be done on small MDPs. MDPs where you have a relatively small number of states where planning is very easy. You can also derive some optimal or near optimal exploration algorithms. And there's quite a bit of work on things like Bayesian model-based reinforcement learning, so similar to the information gain in multi-arm bandits. You can think about information gain if you're doing model-based RL. We're not going to talk about these too much because they're a little tougher to apply in a deep RL setting, so what we'll do is we'll actually take a break and then we'll go to deep RL topics. We'll go to the break now, but if any of you guys have any questions, you can ask me now or come up and ask me. And if not, then we'll be back in 3 minutes. Yeah?
So you were saying that the constant factor, they all have regret login, but there's a constant factor.
Mm-hmm.
So is it the case where in some problems, like one of the sampling methods will perform better, and then another problem it'll do worse?
Yeah, so if you take a look at that empirical exploration of Thompson sampling paper that I mentioned, that's a good example of how one of these empirical evaluations can be done. The constant factor is very difficult to analyze because it depends on so many factors of the algorithm. Like there are many different UCB-style terms that you can formulate that are all log of t. But then the devil's really in the details for the constant factor, and usually people don't bother analyzing that.
Okay, but so it's still not the case that the constant factor doesn't really tell you, I guess, which one to pick. It still depends on the problem, or?
Yeah, it's going to depend on the problem.
Okay.
Yeah. There was a question back there?
Yeah, the initial formula for the regret minimization. Normally, real people don't know their optimal outcome. So how are you maximizing regret other than, you could also have the ignorance is bliss strategy.
Yeah. So the regret is not actually used anywhere in these exploration strategies. Regret is just a quantity that we use to evaluate how good a strategy is. So what we can do is we can basically say that, okay, this exploration strategy is good because it asymptotically minimizes regret. The algorithm itself doesn't actually use regret anywhere, so we don't need to know it in practice. All right, let's continue. So before the break, we talked about bandits, and now we'll actually move into the kind of complex, high-dimensional MDPs that we want to tackle with deep reinforcement learning. And the classes of exploration methods in deep RL that I'll cover are going to basically reflect the three classes that I discussed before. We'll talk about optimistic exploration, where you basically assume that a new state is a good state. And that's going to require estimating how often you've been in a state or the novelty of that state. And typically, this is realized by means of exploration bonuses, where you actually add a term to your reward function to encourage the agent to go into new states. We'll talk about Thompson sampling style algorithms for deep RL exploration. So these are going to learn distributions over one of the things we talked about before, like a Q function or a policy or a value function. They're going to sample from that distribution and act according to that sample. And then we'll talk about information gain style algorithms a little bit at the end. And these are going to reason about information gain from visiting new states. All right, so let's talk about optimistic exploration in RL. We talked before about UCB, upper confidence bound, and optimistic exploration in bandits. And one of the criteria that we formulated was this, that you're going to add to your expected reward, you're going to add 2 times the natural logarithm of how many steps you've taken divided by the number of times you've taken that action, and take the square root of that. So this second term can be viewed as a kind of exploration bonus. So it's saying, okay, your reward is actually, on average, going to be this mu, but we'll lie to you, we'll tell you that you'll actually get a bonus for exploring. And this will incentivize you to explore. So in a bandit setting, actually choosing the action is very easy because you can do this argmax, you can enumerate the value of all of the different actions, and you can just choose the best one. In RL, in an MDP, choosing the best action is not so easy. That's why we had all those lectures in the beginning of the class about policy gradient and the value iteration and so on. So in RL, choosing the action that maximizes reward is not so easy, but we have those algorithms already. So we can actually use those algorithms that we learned about before and just change their reward function by adding an exploration bonus. And we'll basically just use those other algorithms like Q-learning and so on to choose the actions that maximize the reward plus an exploration bonus. So the main thing that we have to do is actually formulate an exploration bonus that makes sense. So there's lots of functions that will work. They just need to decrease with n of a. So basically, things that you haven't visited very much get a bigger bonus. Things that you visited frequently get a smaller bonus. The trouble is that with MDPs, you have to consider how many times you visited a state, not just the action. So in general, you want to use a count for the state and the action. Sometimes you can also use a count just for the state, because oftentimes the actions themselves are not that interesting. Like if you're playing Atari games, there's only a few actions, and you don't really care which button you're pressing. You just care about which state that you're in as far as novelty. So most of the theoretical stuff and a lot of the foundation for these kinds of algorithms is going to assume that you're counting S's and A's. But for the simplicity of notation, I'll just use n of s in this analysis. And actually, many practical algorithms also just use n of s. So if you can somehow count how many times you've been in each state, you can use that to formulate an exploration bonus in an MDP, add it to your reward function, and use it within a standard reinforcement learning algorithms. So you might just say, my new reward function, my inflated reward R plus, is just my old reward function plus some bonus, which is a function of n of s. And the bonus might have, for example, this form. Does anybody have any question about reward bonuses, exploration bonuses. Yes?
So this only applies to discrete cases, right? Because if you're
Yeah, so that's what I'll talk about next. Okay. All right, so the bonus just has to decrease with n. There are many different options, and I'll show some options later on. And then you just use R plus instead of R with your favorite model-free RL algorithm. And that's the high-level scheme of most of these exploration bonus methods. So now, coming back to your question, well, first some of the pros and cons. It's a simple addition to any algorithm, but you need to tune this bonus weight, so typically you'll have some weight that trades off the B from the R, and there's a little bit of tuning that has to go in there. All right, so here's the answer to your question, the trouble with counts. What's a count in a big, high-dimensional MDP? Like, how do you actually count how many times you've been in a state? So if you have your Montezuma's Revenge, you might say, well, let's count how many times the little guy has been in each position in the world. The trouble is that the little guy is not the only person that matters. There's also the skull. So maybe let's count how many times the guy has been in a particular position and the skull has been in this other position. But then you have to consider the key, and then you have to consider the number of lives and a whole bunch of other things. So in reality, with all these different things and little animations on the screen too, you don't even know if this thing matters, but it changes all the time. So if you go to a continuous setting, there the story is even more dire. Like maybe the arm is in a very similar place as it was before, but because everything is real valued, because there's all these Cartesian coordinates and so on, maybe you'll never actually be in the same exact spot twice. So you'll never actually see the same exact thing twice in any of these large MDP problems. This one is technically discrete, so it is technically possible to see the same thing twice, but there's so many different pixels on the screen and so many little irrelevant animations and so on that purely counting how many times you've seen any given thing is just not that useful. And in these continuous settings, it's basically impossible. Even if two states are functionally almost identical, they're probably numerically different. So it's not enough for us to just count. We can't just have a gigantic table. We need to do something a little more clever. All right. There is a little bit of a saving grace, which is that some states are more similar than others. Like if we can look at different pictures of this hand holding a hammer, we can figure out that these two states are more similar and these two states are more different. And we can look at this guy, and our intuition is pretty strong that if the guy was to move a little to the left, that's not that different, but if you were to jump all the way down, that's pretty different. So there's some kind of similarity between these states, and it seems like we ought to be able to use that to produce some kind of continuous version of these counts. So what we're going to do to introduce a continuous version of a count is we're going to fit a density model or a generative model. So we're going to take some kind of generative model p theta of s. So there are many different models we can use, and we'll talk about a few classes later, but it's some kind of model that can represent the density p theta of s. We'll fit that model to our data, and then we'll use this to recover something that looks like a count. It won't actually be a count, but it'll be a pseudo count. It will look like a count. So p theta of s might be high even for a new s that we've never seen before if that new s is very similar to other s's that we've seen. So if you saw the hand in one pose, you saw it in a different pose, and then it's somewhere in between, well, you might say, well, this probably still has pretty high density because it's similar to these other things that we've seen. But if it's a totally different pose, then you say, OK, this is low density. So now the question that we have to answer is, can we use p theta of s to get something that looks like a count, to get something that we can use within a count-based exploration bonus algorithm? So before I get into that, does the notion of fitting density models make sense to everybody, or does anyone have any questions about it? OK. So let's talk about counts. If we have small MDPs where counts actually make sense, then probabilities and counts are related by a simple formula. So the probability of a state is just the count of that state divided by the total count, the total number of states that we visited. So this is just how probabilities work, right? So the probability of a state is n of s divided by little n, and little n is the total number of steps that you've taken. So this is also the visitation frequency of s. This is going to be a probability or probability density. This is the count, and this is the total states visited. And then after you see some new state s, then you update your probability because you have to increment the count of that state, and you also increment the total count. So we're going to use p prime of s to denote the probability of that state after we've seen it, And after we've seen it, both the top and bottom get incremented by 1. So if we were counting, and counting was a legitimate thing to do, these equations would hold. So now the trick that we're going to play is that we're going to make p theta of s and p theta prime of s obey these equations. So p theta prime of s is our density estimation model after we've updated using the newly seen state s. So this is exploring with pseudo-counts, and you can read more about it in this paper by Bellmer et al. So the idea is this. I'll just present the outline of the algorithm, and then I'll explain the details. So you're going to fit your density model p theta of s to all the states in your data set D that you've seen so far. So this is basically like your replay buffer. You fit your model to everything you've seen so far. Then you take a step, I, and observe a new state, Si. And then you update your model. You basically fit it to the union of all your prior states and this new state. And that gives you p theta prime. And now you're going to use p theta and p theta prime to estimate a pseudo-count n hat of s. And we'll call it a pseudo-count because it looks like a count, but it's not a count. And then we're going to set our reward for that state to be the actual reward, Ri, plus a bonus that is a function of the pseudo-count. So this is a pseudo-count, and then we repeat the process. So then we take our theta prime, we make that be theta, so that means we get the new model, and then we repeat. All right, so now the critical thing we have to do is figure out how to get that n hat. And the way that we get the n hat is by using those equations that we saw before. So we no longer can compute actual counts because no state is visited twice, but we'll just say, let's pretend that it's a count. We know that a count satisfies these equations, so let's figure out some count that satisfies these equations. Let's figure out some count such that p theta of s is equal to n hat over little n hat, and p theta prime of s is equal to n hat plus 1 over little n hat plus 1. So we have two equations and two unknowns. We don't know this thing and we don't know this thing, so we'll just solve for the two unknowns because we have this density and this density. And I did the algebra for you here. If you want to know what the answer is that big N hat is equal to little n hat times p theta of s, and little n hat is this slightly more complicated function of the new and the old density. So you can crunch through the math, and you get a new pseudo-count for that state, and the little n, which you just need to compute it here, put it in here, and then you can discard it. So you don't actually store big N hat or little n hat. All you store is theta and theta prime, and you just compute the n every time you visit a state by solving those equations. Yes?
I'm sorry, what's theta n hat again?
So theta, these are the parameters of your density model. So if your density model, for example, is some kind of big neural network, the thetas might be the weights in that neural network. And I'll talk about particular models next. And then theta prime are the parameters of the model after you've updated it on this new data set where you have all of your old data plus the new state.
And what's n hat?
So little n hat is the total pseudo-count. So this is, in the same way that big N hat is the pseudo-count for a state S, the little n hat is the pseudo-count for the total number of steps you've taken. So it doesn't really have any concrete meaning now that it's a pseudo-count. It's just there to solve the equations. Any other questions about this approach? Okay. So this is actually a pretty good exploration method. But before we can actually use it, we need to make a few choices. First, we need to choose what kind of bonus we should use. So there are lots of bonus functions in the literature, and mostly they're inspired by optimal exploration methods for bandits or small MDPs. So it's very hard to prove anything about a particular exploration bonus when it comes to these really complex MDPs that we use in DeepRL. But for small MDPs or bandits, you can actually prove some bounds on these bonuses, and you can use them as inspiration. So here are a few examples. This is the UCB bonus that I've written now in terms of little n and big N. This is the particular bonus that's actually used in that Bellmer et al. Paper. So it just replaces this term with a 1. This is another bonus that you can use proposed by Coulter and Ng, and there are many other options. So this is the one used by Bellmer et al., and you can look through the literature and find some other examples. So for big MDPs in DeepRL, choosing the particular form of the bonus is largely an empirical question. but you can use the theoretical grounding from bandits and small MDPs as inspiration. So does it work? This is the evaluation from the Bell-Meredal paper. And I can guide you through the qualitative one and then the quantitative one. So the qualitative evaluation is on Montezuma's Revenge. And remember how I mentioned that the game consists of these rooms that are arranged in kind of a pyramid shape. So you actually start up here. The exit is down here. So the picture on the left is showing the rooms that were visited by, in this case, Q-learning without any exploration bonus. And the one on the right is showing the rooms that were visited by Q-learning with the, I'm sorry, I think this might actually be A3C. By A3C with the exploration bonus using the square root of 1 over n of s, where n of s is the pseudo count obtained through the density model. And then the results up here show the quantitative results. So I don't actually remember what optimistic means, but the light green line is 1 over square root of n. That's the one that they're using. And the dark green line is dqn. And you can see that there's actually, dqn doesn't even show up here. I think it's just flat down on the bottom. So on many of these games, the exploration bonus actually yields a pretty substantial improvement. So that's nice. What kind of model should we use? So we need this density model, p theta of s. There are a number of different choices. And one of the things that we have to consider, if you look through the literature, there are many, many different choices for generative models in deep learning. So if you've heard of variational autoencoders or generative adversarial networks, these are all problems that fit a p theta of s. They fit a generative model that will generate observations, whether they're images or continuous valued things. However, if we're talking about exploration bonuses, we have slightly different requirements on these density models than is typical in the literature. So we need p theta of s to be able to output densities, but we don't necessarily need to sample from it. And usually, when you're talking about density models, you oftentimes want the opposite. If you want a generative model, oftentimes it's because you want to sample from that model. And in fact, you can build very good generative models like generative adversarial networks that are very good to sample from, but it's very difficult to get a density out of them. For exploration, you actually need the opposite. You don't necessarily need to sample from this thing, but you do need it to give you a quantity. You need to give you a density. So it's the opposite consideration for many popular generative models in the literature, even though technically it's the same type of model. So the particular model used in the Bell-Meredal paper is a little peculiar. It's what they call the CTS model. And the CTS model basically writes down the probability of all the pixels in the image as a product over all the pixels of a particular factor. And the factor is just the probability of this pixel given its top left neighbors. Why do they do this? Well, because it's relatively easy and it's a little bit arbitrary. But it's pretty easy to write down this model because it's just a product of independent factors. It's not a very good model of images because the pixels in an image don't really have this independent structure. But it's easy to write down, and it gives you some kind of quantitative density. But there are many other models that you could also use. So you can use stochastic neural networks. You can look at compression length with some compression methods. And a particular method that I'll describe a bit later is something called EX2, which is actually an implicit density modeling algorithm that uses discriminators. So there are a number of different choices you can use for these models. CTS is the particular one used in that paper. I won't go into that too much, but you can look in the paper for the reference. All right, so any questions about pseudo-count-based exploration before I move on to the next section? OK. So next, I'd like to tell you about another work that also uses count-based exploration, but in a slightly different way. So this is a paper by Tang et al. Called hash exploration, I guess, a study of count-based exploration. And in this paper, they have a slightly different idea. So what if we still count states? What if we use actual counts instead of pseudo-counts, but in a different space? So counting the number of times you've seen a particular image, that's not a really good idea because you won't see exactly the same image twice. But maybe you can count something else. So here's the idea. What if we compress the image S into a k-bit code via some compression function phi, and then we count the number of times we've seen that code? If we choose a small enough number of bits, then we're bound to see a bunch of hash collisions, and we can count those. So if basically we can directly control how many collisions we get just by shortening the code. And if we compress the image into like 8 bits, we're bound to see tons of collisions. So then we'll actually get meaningful counts. So the shorter the code is, the more hash collisions we'll see, and the more meaningful the counts will be, with the caveat that similar images don't necessarily get compressed into similar hashes, or into the same hash. So similar states get the same hash? Well, maybe or maybe not. It sort of depends on how your compression algorithm chooses to compress these particular images. Because the similarity you care about is sort of the semantic similarity, the functional similarity between the states, which might not necessarily be exactly the same as the similarity exploited by the compression algorithm. So this is where things get a little bit heuristic. But one of the things that you can do to improve your odds of getting a better, more useful compression is instead of using some off-the-shelf compression algorithm, instead of using gzip or something, which you can do, you can instead learn a compression. You can actually train an autoencoder that takes in the state, let's say takes in the image, and it's trained to output that same image, but in the middle of that network, there's some kind of bottleneck. So maybe there's a bottleneck with 512 sigmoidally gated units. And you can use the activations of those 512 sigmoidally gated units as a binary code, for instance. And the more you crunch down this bottleneck, the smaller your code becomes, and the more hash collisions you start to see. So so you might hope that if you're dealing with image data and you use this autoencoder with maybe some convolutional layers, the encoding that you'll get will be a little bit more cognizant of the similarity between images. Of course, there's no guarantees here, and this object is not necessarily a functional object. It's not looking at the functionality of the different states. It's not looking at whether the skull is about to kill you or not. It's just looking at similarity between images. But if similarity between images is something that you believe is a good proxy for state similarity, this might give you a better encoding that you can then hash and count. So does this method work? It works reasonably well. It's a little hard to see on this screen, but the green line on Montezuma's Revenge, the really good one, this one is actually using some hand-designed features and then compressing those hand-designed features. So it's getting quite a bit more knowledge about the game than the count-based method before. So in that sense, it's not working quite as well. The blue one is the one that's using the raw images, but it's still doing better than no exploration bonus at all. And it's quite simple. So in comparison to the pseudo-count-based method, which requires this fairly elaborate generative model and a pseudo-count and the solution to those linear equations, this one just requires hashing and maybe an autoencoder. So it's kind of a simple approach that still produces some improvement. There was a question?
Yes. Does this actually pull all of the counts into a separate table and break the end-to-end-ism that you might like?
Well, it does pull them into a table, yes. So does it, what does it lose in doing this? Well, what it loses is that the hashing necessarily has to discard some kind of information. So if your image contains n bits and you compress it into m bits where m is less than n, something has to go. So that means that there is always a danger that there will be something relevant in the image that gets hashed to the same code as an image that doesn't have that relevant thing, and then you won't realize that that state is novel. OK, so that's hash-based exploration. Does anybody have any questions about this method? OK, so I have a little bit of time left, and I think in that time I have enough time to finish the last density-based method, and then I'll finish the rest of the material on Wednesday. So the last method I want to cover is using implicit density models with exemplar models. So this is from a paper by Fu et al. Called EX2, Exploration with Exemplar Models. And the idea in this work is to exploit the fact that we don't need p theta of s to necessarily be good for sampling. In fact, we never have to sample from it at all. We just need it to give us a number, a density number. And we can actually exploit this to construct a very peculiar kind of density model that is, in practice, easier to train on images than general purpose generative models like VAEs or GANs. So the idea in this method is the following. If we see a new state, let's try to somehow compare it to old states we've seen. And in particular, we'll say that a state is novel if it's easy to distinguish from other states we've seen in the past. So if you just build a classifier that tries to classify this new state from all the other states you've seen before, if it's easy to build that classifier, then you've probably seen something new. If it's very hard to build that classifier, then this new state you're seeing is probably similar to the old ones. So for each observed state S, we're going to fit a classifier to classify that state against all other states in the past in our data set D. This is a very peculiar classification problem. It's a classification problem where there's two classes. The positive class contains only one sample, which is S, and the negative class contains tons of samples, which is everything in D. But if you can build this classifier, then you can use it to obtain a density. And this is how you obtain that density. So here, D of S, this is a very peculiar number. D of S is the probability that the classifier assigns to S of being in the positive set. The positive set consists only of S. The negative set consists of all of D. And the subscript S means that this is the classifier trained for S, and ds of S is the probability that that classifier assigns to S of being in its own set. If this sounds a little weird, it's because it is, and I'll explain why it's weird on the next slide. But if you have ds of S, then you can compute a density using this formula. So ds of S is the probability that the classifier assigns that S is positive, where the positives contain only S and the negatives contains all of D. So this is our formula. And the way, the peculiar thing about this formula is that the classifier is answering a very weird question. The classifier is just saying, is S equal to S? That's a very strange question to ask the classifier to answer. Like, yeah, of course S is equal to S. It's the same thing. But here's why this idea actually works. If we had a small MDP, where we might actually see the same state multiple times, then the data set D might itself contain some copies of S. So if our MDP just has two states, and we visited one of the states 10 times and the other one 9 times, then the 10th time we visit that second state, there will already be 9 copies of it inside D. So the classifier then is trying to solve an ambiguous problem. Basically, the optimal classifier should not actually assign a probability of 1 to S, because it's trying to say, what's the probability that S is in the left set or the right set? The left set consists entirely of S, and the right set might consist 50% of S. So the right answer is not to say that the probability is 1. The right answer is to give the probability according to this formula, 1 over 1 plus P of S, where P of S is the actual density of S. So if you have a small MDP, then you can actually recover a density from this classifier, because even the optimal classifier will not assign a probability of 100% to S, because S might also appear in the negative set. And this is coming back to this point I mentioned before, where you can use these smaller problems, bandit problems, and small MDPs to build up your intuition about how exploration algorithms can be designed. So here we can use the small MDP to build up our intuition, and we can show that, in fact, in a small MDP, this notion of an exemplar classifier actually makes sense, even though it seems to be doing this paradoxical equality test. Because, in fact, it's not an equality test. It's a set membership test, and the set membership is not 100%. OK, so that's in a small MDP where you visit a state multiple times. So this thing can be used to recover this density, and that's just by algebra. So in reality, each state is, of course, unique. So if you have a unique state, if you have a state you've never seen before, if all your states are unique, then your classifier can overfit. And it can actually give you 100% and answer this question of S equals S. So what you do in that case is you have to regularize your classifier. And there are a number of different regularization techniques that basically force the classifier to be a weaker classifier so that it smooths out the distribution, and these are discussed more in the paper. So in practice, the classifier needs to be regularized when you train it on images or continuous states. Now, the other issue with this method is that you're training a classifier for every state you see. So isn't one classifier per state kind of a bit much? Like, that's a lot of neural networks you're going to be training. In reality, you can actually train one amortized model. So it's amortized, meaning that it's amortized over all states that you'll be seeing. And this is basically a kind of a parameterized classifier. It's a classifier that takes 2 inputs, the image you want to classify and the image that's in the positive set. So it's this kind of Siamese network that takes in 2 images, the thing that defines the set membership and the thing that you're trying to classify, and it outputs the class label. And then you only have one network that you have to train. So it's a kind of comparator network. It's a network that's answering this fuzzy S equals S question. And the method does indeed work on image inputs, so there's some evaluation in the paper. This is an evaluation on a game called VizDoom. This is a benchmark task based on the Doom video game. And here the goal is to start off in this blue, at this blue spot, navigate a series of rooms and reach a target indicated in green, where the reward is only provided once you actually reach the target. So you have to sort of blindly navigate these rooms, not knowing what the reward is, until you stumble on the answer. And this kind of novelty detection through density modeling helps a lot there, because it tells you when you see a new room that you're seeing something interesting. So every time you see a new room, you get incentivized to go there more often. And if you see an even more novel room, one that's very different from what you've seen before, you get even more incentivized to go there. So this kind of task is basically impossible without exploration, but with a good novelty-based exploration strategy, it can actually be solved. OK, any questions about this method? Yes?
So does your classifier, do you featurize the image, or you just give it raw pixels? Or?
No, this is using raw pixels.
Okay.
Yeah. The nice thing about this is that the classifier is just trained discriminatively. So discriminative training of convolutional neural network classifiers is pretty easy. All right, so we'll conclude our discussion of exploration on Wednesday because we're out of time. So I'll see you all then, and also homework 4, don't forget to turn that in on Wednesday night.